Hi everyone, welcome back. Welcome back to Talk Math with your friends. Our speaker today is Dr. Matthew Macauley. Dr. Macauley is a professor of mathematics at Clemson University. He's the author of some of those really beautiful algebra diagrams you may have seen floating around Twitter. And today he will be talking to us about teaching group theory and purple unicorns. So everyone, please join me in welcoming Dr. Macauley.
Thank you, Ken, and hi everybody. I'm Matt or Matthew. I have no preference between the two. You can call me either one, but I prefer informal over formal. So we're all colleagues. Okay, so I have a talk is about visual group theory, and I am choosing to go to doing breadth rather than depth. So instead of a couple topics in detail, I'm going to try to cover a whole bunch of stuff. I'm going to go way too fast, but they're sort of loosely related. So if you miss something, you can get the next one. And the idea is to sort of show off a whole bunch of really shiny objects. And maybe a couple of them you'll look at and like, and we can talk about later. Yeah, let's get started. So what is a group? I got a couple of these slides, wrong answers only. This is actually the right answer, but most text, pretty much every group algebra textbook has very few pictures, if you've noticed. And so you'll see definitions like this, and this is often done in day one. To picture math majors who, maybe not like us, grad school bound, but ones who took calculus a year and a half before, and the first day they see this complicated definition. What is a group? And then, oh, what's an example of a group? The symmetries of a square. Like, where did that come from? Now, if you don't have pictures, you don't have that many groups that books and classes have as examples. You've probably seen the Quaternion group, I, J, and K, where I squared and J squared and K squared are equal to -1. And then you have I, J equals K, and J, I equals -K. So this is a standard example of a group of size 8. You also have the Dihedral group, which is the symmetries of the square. And these are typically given with, these are called presentations. It tells you the generators, it tells you the relations, and then it's not clear how big this is, if this is finite or infinite or what. But this is what you have to work with. And so all the sort of things you do in group theory are given these presentations. Now, there's a way to visualize these presentations. Well, before I do that, here are some groups that I claim. So I'm old, I'm in my 40s. As a late Gen X or early millennial, whatever in between, there was this catalog that I get once a month. It's called Things You Never Knew Existed and Other Items You Couldn't Possibly Live Without. I don't know if anyone else knows that catalog, but I love that. I spent way too much allowance money on like stupid little gimmicks. So this is groups you didn't know existed and others you couldn't possibly live without. So you've probably heard of the abelian group and the dihedral group, but you've probably not either heard of these or are not familiar with things like the dicyclic, semidihedral, semiabelian, and Pauli groups. And I know this because I teach graduate algebra, and I did not know what any of these groups were a couple of years ago when I was teaching that course. But I want to convince you by the end of this talk that you need to have these groups in any algebra course. These are fundamental for examples, really illustrative examples of things that you just don't get with your standard, these two boring guys. So, okay, so here's a Cayley diagram. So this is what's called a Cayley diagram, and it's basically a visualization of a presentation. So so the symmetries of a triangle. Here's a triangle. There's 6 symmetries. You can rotate it 3 possible ways. You can reflect it 3 possible ways. And then if you rotate it, so if you take this thing and you rotate and then reflect, that's the same thing as if you reflect and then rotate twice. So this R is a 120-degree rotation, counterclockwise. So R squared is a 240-degree rotation. Everything's going to be counterclockwise, or a -120-degree rotation. Either one of these is the same. So it doesn't matter how you get there, it matters where you start and where you end up. So this encapsulates all the symmetries of the triangle. I'm going to call this one my home state. I'm just going to think of it like a solved Rubik's Cube. And then everything else, this is like a group calculator. It tells you, how do I get from here to here via these basic moves? Now, what we usually do is we take our home state and we put the identity element here, like 1, and then we label everything else with group elements. So this is what you get to by rotating. This is what you get to by flipping about the vertical axis. This is what you get to by doing a rotate and then a flip and so forth. So this is the object that these objects are what are going to be throughout this talk. These labeled Cayley diagrams, how you should think about them. This doesn't encode anything more than a presentation. It's literally just a way to visualize it. It's like a group calculator. If you want to know what is r squared times fr, you just start here and you do r squared times fr. Oh, that's equal to rf. Okay. Oh, hey, Alex, I just saw you in the chat. No, you're coming. Okay, so here's an example. There's other groups I can show the class, like I do this the first day. I said, here's a different group. The operations are, you can, S is swap the first two squares. So S takes these two and swaps to that. And then T toggles the color of the first square. So black becomes white. And so these generate a group. This is the Cayley diagram. And I'm not going to tell you what this group is. Some of you might recognize it, but it's a fun exploratory exercise to figure out what this is. So again, I'm going to go breadth over depth. So I'm going to go through a lot of material, not with that. And I'm happy to talk, and I can send out the slides if you guys want, so you can go back and look at the stuff. But my goal is to cover everything rather than doing things properly, because I'm trying to cover like a whole semester's worth of algebra in like 50 minutes. So it's not going to be easy. Here's a good example that you normally don't see in an undergrad course, a frieze group. So a frieze is an object like this that has a one-dimensional. It has symmetries in one dimension. So this thing you can slot, you can translate as much as you want to the right. And you think about what the symmetries of this are. There's a single vertical reflection. There's also infinitely many translations to the right or left. So I'm going to let T be a minimal one. There's horizontal reflections across any of these axes. There are there's 180-degree rotations about any of these points right here. You can rotate 180. And then there's glide reflections. This is what you do when you do a translate and then the vertical flip. You can do those left or right. So the symmetry group consists of this unique vertical reflection and then these four infinite families. And so there's a lot of ways to generate this. And what this means here is that this group is generated by a translation, a horizontal flip and a vertical flip, or by a translation, a horizontal and a rotation. There's a lot of ways to do this. Now, if you want to get rid of the vertical reflection, you can do that in a number of ways. You can, for example, actually, before I get there, so in class, we play around with how these things are related. Like if you if you do a horizontal flip and then you do a translate, that's the same thing as flipping about a different axis right there. And the same thing with the rotation. So I have a whole homework assignment where we play around. I mean, so here's my first homework assignment. And on this, we have, I have them labeled, here's a Cayley diagram, and I have them label these things with which of these nodes represent rotations and reflections and things like that. And then they explore what does it mean to be conjugate? Why are all the rotations conjugate? So they understand what conjugates behind conjugacy before we ever get to anything like that. So if I get rid of half of these triangles, now I've wiped out the vertical symmetry. And if I do this, along with it, I wipe out half of the rotations and half of the reflections in the process. So this is a different frieze group. Here's a Cayley diagram, but there's other things I could have done. Again, this is why I'm going fast. I could spend like 10 minutes on this slide if I want to. I could instead wipe out, starting here, I could wipe out all of the rotations or all of the reflections. So if I wipe out all of the rotations, I get this frieze. If I wipe out all of the reflections, I get this frieze. And if I wipe out both, I get this one, and this is an abelian group. So it turns out there's only 7 of these things, but it's a really good way to introduce groups before, in the first week, before, I think, before normally. And you really need to, you can't really do this without visuals. I mean, you can, but most of the students are not gonna get it. So here's a Cayley diagram of what this frieze group looks like. So you can close your eyes and pick one of these things and call that the identity. And then this is a vertical reflection. This is a translation. This is a vertical reflection and translate. So this is a glide reflection. And then you can keep labeling it like that. So this is T squared, T -1. And so I'm going to keep going because I have a lot to cover. So the Quaternion group, this comes up in any undergraduate group theory course. So this is that IJK, and you can think of as like I is the square root of -1, but j is like a different square root of -1, and k is a different square root of -1. So here's a Cayley diagram of this. You can see how these things are put together. And this is called a Cayley table. It's like a multiplication table. And I've arranged it in a way where you can see, and the students can see right away, like there's something going on here. This is like, if you squint your eyes, you get a table of the Klein 4 group, which is, it's a symmetries of a rectangle. So there's 4 symmetries. You can there's doing nothing, there's the identity, there's a vertical flip, there's a horizontal flip, or a 180 rotation. That's the Klein 4 group. And so you squint your eyes from here and you get that. So I put stuff like this on the first few homework assignments. I have them discover, this is the idea of a quotient. And a month before we ever see what a quotient is, my students are actually doing this on their homework. Later this was formalized via a homomorphism. So I am not paying attention to the chat. So if there's something, feel free to unmute yourself, ask me a question, etc. I thought I would, but I'm not that good at multitasking.
All enjoying in the chat how lovely your pictures are. So
okay, thank you. And I'm happy to share the tech code with anybody.
Yeah, there was a request. There was a request for that. So send it to us.
Cool.
And we'll get it posted somewhere sometime.
So now one thing you may ask is, well, why not can you define groups in terms of pictures, in terms of either a table or in terms of a Cayley diagram? Like, why does this not just define it? Why do we need those 3 axioms, as inverses, associativity, etc.? Why do you need those? And here's why. These guys look like a group, they quack like a group. These are not groups. This table looks like a group. It's called a Latin square. It's not an associative binary operation. This one's even weirder. I didn't know this existed until like 2 years ago, and I was trying to make this as a semi-direct. I was like, why is this not? This is a group. What group is this? And then I looked at this and I realized, well, this is not abelian, right? Because blue-red is different than blue. The order matters. Red blue is different than blue red. But look at this. If you take red blue and you iterate that, red blue, 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 you get everywhere. So this group is if this were a group, it would be generated by it would be cyclic, but it's also not abelian. That is a problem. Cyclic groups are not abelian. So this is a great example to explore. Why is this not a group? And this is why you need, students say, why do you got to prove things in formal? This is why, because that ain't going to work. And it's fun to explore why it doesn't work. You can create a presentation with this and figure out what group that is. And it's a smaller group, and I won't tell you what it is. But anyways, it's a fun thing to explore. So now, another important thing that I always emphasize is you can represent these symmetries with matrices. So throughout this talk, think about so when I say a rotation, you can think of this as as multiplying by root of unity, which is like a 1-by-1 matrix in the complex plane. But more useful to think of it as a 2-by-2. This is a complex reflection. So it's a map from C2 to C2. And you may say, well, why is there a bar here instead of a negative sign here? Because you can get rid of the bar, it still has order n. You can put a negative sign here, it still works. The reason is because if you take this rotation matrix with this is like the reflection matrix. It swaps the first and 2 coordinates, that these things together behave like the dihedral group. These things generate 2n matrices that have the same relation. This is the dihedral group. So throughout this talk, this is going to be our rotation matrix, and this other one is going to be our reflection matrix. Now the quaternions can be represented using the 8 matrices as well. So this is plus or minus the identity. Here you got that same rotation matrix, but for a special case of n equals 4. Now this is a different matrix. So this is like your I, this is like your J, and this is your K. So the quaternions, you can think of it as these 8 matrices. Now, here's something that just never comes up in an undergraduate algebra course. And in any algebra book, if this is there, it's buried in the exercises or an obscure example. But has anyone ever thought about taking the quaternion group like this and taking this matrix? And what's I here? I is a 4th root of unity, right? Well, what would happen if you replace that with a different root of unity, like a 6th root of unity? What group would you get? Well, here it is. So let's replace that with, if you do it with a 6 root unit, well, if you do it with an nth root unit, you get what's called the dicyclic group. And so this is the dihedral group, D6. This is the symmetries of a hexagon. So rotate, flip is flip, rotate the other way. And the dicyclic group, you remove these blue edges and you like rewire them this way. This is the dicyclic group. And you know, you can get rid of these blue edges and ask how else can you rewire this? So this is the dicyclic group. This is the dihedral group. I'm going to show you the best way I think to think about the dicyclic group. Here's another way to think about it. Oh, so take remember the quaternions? You got I, J, and K.
Mhm.
I is in the unit. I is on the complex plane. It's on the unit circle. It's right up there. What if you replace I with a different root unity? Here, let me just show you that picture right there. So I would normally be here, but now we have, this is a 6 root unity. And multiplication behaves just as it normally does. So this complex number times J is that. Now, how many of us have gone through an algebra course or taught an algebra course, maybe at the graduate level, I'm raising my hand, and did not even know this group existed? This is such a natural thing to look at. I taught this class as of 3 years ago, and I didn't know this group existed, or I'd maybe heard about it once. But it's such a beautiful, and there's this, if you just do it in terms of the presentation, it's not going to make, I mean, how do you motivate that? How do you understand what that is? I had seen that before, but I didn't know what that meant. This is what it means. And you can see things, there's really cool things you can see, like this is generated by R and S. But it's easy to see with this picture that it's also generated by R squared and S. Because if I can do R squared and S, I get this column, and now I can go up here and I'll get this column, and then I go here and I get this column. There's so many wonderful things you can do with this. And what I do in my class is let me see where I can find this. So I take this group, more on these later. Oh, actually, I do not know. You know what? I'm going to do this. I'm going to go back to these later. So here's another way to view this group. So rather than like, think of this as the roots of unity, and think of these as the roots of unity multiplied by J, the imaginary number and the imaginary number. Yeah, this is why engineers should not use J for the real imaginary number. You know what I mean. So if you rewire this thing, so you've got these like this. Now this outer ring, these are the powers of J. This is the powers of J. So J squared, J cubed. These are the powers of J times zeta. This is the powers of J times zeta squared. And as you go in, you are getting powers of zeta. So you got powers of J as you go around, and you got powers of zeta as you go in. So this is another way to see it. And you see other structural features in here that you don't see in the other picture. And now if the number of vertices is a power of 2, this is called a generalized quaternion group. And I can talk about more. You can think of all of these as generalized quaternions, but this is a real generalized quaternion group for extra reasons if the number of vertices is the power of 2. And I can give you a number of reasons why really nice things happen when this happens. But moving on. So what we basically did was generalize the dihedral group. If you think of this picture, this is a way to generalize the dihedral group. I erased the blue edges and I rewired it. Well, there's other ways you can do this. What if you erase, instead of erasing the blue edges, what if you erase these red edges and ask, how do I rewire those? That's something you probably never thought about if you don't do it visually, but it's a very natural thing to ask. And well, here's one way. So you can connect this thing. So you go halfway across -1. And if you do this, you get the semidihedral group, which in any sort of book is going to give, they're going to give you this presentation. What does that mean? Why are we doing it? How do you understand this? Well, here's how you understand it. And you can see how this thing generalizes. And this works for any power of 2. And it's not obvious why it doesn't work for n equals 6 or n equals 12, but it works for powers of 2. We can explain that with these questions I'm throwing out there are fun, like student projects or like things. I didn't know the answer to that one, so I put it on the homework this semester. And we figured it out via homework. What happens if you do this with n equals 6? And the reason why it's nice is because we have matrices. So we can always just take the matrices and say, what group is this? Now here's a different one. This doesn't really have a good name. Dumb-to-Foot says sometimes it's called a modular group, which is a bad name. I can't tell I don't think that many resources call it that. There's other random names that it's given. A couple of weeks ago, my student, Corey Andrews, I suggested, I told my class, I was like, we need another name for this. And so he's like, what about semiabelian? And I love that name for reasons, and this is connected to, maybe I can hopefully I'll show you why later, but let's call this semiabelian for now. It's the same thing, but instead of wiring this to halfway across -1, we go halfway across +1. So this has almost the same presentation. The only thing is that instead of a negative sign here, you got a plus sign here. Again, without a picture, like what the heck does this mean or represent, and why do we care? So moving on. There's one more way to rewire this. Obviously, you can just do it this way, but this group is abelian. So this is C8 cross C2. And for any group, you can always draw what's called the cycle diagram. And so this is there's no arrows on here. This is the identity. And R generates an 8 cycle right here. A cyclic group of size 8. This element generates a 4 cycle. This element here generates an 8 cycle. And this diagram sort of tells you how these are intersect. So this element has order 2. This is a 2 cycle. Here's another 2 cycle. This shows you how all of the cyclic groups in here are put together. And I don't have time to sort of dive into this, but anyways, what's amazing is that if n is a power of 2, or if the number of vertices is the power of 2, these are the only 4 possibilities for how to complete that diagram, no matter how big n is. How do you rewire these inner arrows? You can either go forwards, you can go backwards, or you can go halfway across -1 or halfway across +1. And you can understand this if you dive into semi-direct products and at an undergraduate level. I don't have time to go into that, but it has something to do with like what semi-direct products are there, which has to do with the multiplicative group mod n. So anyways, here are these dihedral, semidihedral, and semiabelian groups. Here are their so-called cycle diagrams. So the dihedral group has this big cycle of size n generated by any rotation of 2 pi over n, and then all of the reflections generate these order 2 subgroups. The semidihedral is a little bit different. It's got this, all of these have this big cycle of size n, but now that there's these other cycles of size 4 right here that you don't have over here, and you only have 4 elements of order 2. And the semiabelian looks like this. Now, we've seen this before. This is the same cycle diagram as the actual abelian group, which is why I love that name. This group and this group have the same cycle structure. They have the same subgroup structure. They have the same subgroup lattice, but they look very different. You wouldn't have guessed that, right? Just naively, I would have looked at this and say, that group looks almost the same as that one. They probably have the same structure. That's not the case. These have very different structures, but this one has a very similar structure to the actual abelian group. So again, I'm covering a whole semester of group theory in like 40, 50 minutes, and I'm going fast, but I'm doing breadth over depth. So remember I told you groups you didn't know existed and others you couldn't possibly live without? These are, I cannot imagine teaching an algebra course anymore without using these all throughout. These are wonderful examples. You can think of them in terms of matrices. Oh, and by the way, here are the presentation. So if you modify the presentation for the dihedral group if you replace the reflection with this is that, remember, imaginary matrix for G, this is like J in the Quaternion group, you get the dicyclic group. But if you replace this thing with this is like a twisted reflection matrix, somehow I don't fully understand, you get the semidihedral group. And now if you replace it with this version, you get the semiabelian group. So all of these are very similar. Now, one thing I didn't, I've been talking about taking the dihedral group and like tweaking this, replacing this matrix, or replacing, what if you take the Quaternion group and what if you threw in the reflection matrix? Now think about what this reflection matrix does. If you multiply this by a 2x2 matrix, it either swaps the rows or swaps the columns, depending on whether it's the left or the right. So think of this thing as allowing you to swap rows or swap columns. And if you take the Quaternion group and you throw in this reflection, you get what's called the Pauli group. And here's the Quaternion group sitting right here inside. And this is almost like, these are like square roots of the elements of the Pauli group. I think this is a beautiful group. And again, I had heard of this only a couple of years before, and only about a month ago did I actually do a deep dive and figure out what the heck this was and why it is what it is. Now, there's something else we can do. Remember how we replaced I with a higher root of unity? Let's do that again. Let's replace this with one of those, with this reflection matrix. And now you get this family of groups for any even n. So, and it's fun to look at at the subgroups in here and ask what's the center? What properties what are the cosets, et cetera. So this is something with, if you remember the original, this is how you define that group. Like how do you understand that or motivate that or explain that or even use that as an example? You really don't, unless you have pictures. Okay, so moving on. One thing I do early in my class is I construct semidirect products. So
I have a question before you go on.
Say what?
So I have a question before you go on, because it looks like it's about to transition. So I haven't thought about Cayley graphs in a while. These pictures are not just the groups, but they're the groups and the generators, right?
Yes.
So without a presentation with specific generators, so is this equivalent to all of group theory, or is that a meaningful addition to know what your generators are?
So different generators give you different diagrams. So this group right, so I wouldn't say this, but this group right here is actually the dihedral group, the symmetries of the square generated by this reflection and this reflection. So this looks very different than those dihedral groups, Cayley diagrams that I've been showing you, because the generating sets are different.
Right.
So the generating set absolutely gives you a different perspective on the group. I mean, all these things are like, this is literally just a way to visualize a presentation. It's nothing more. It's just, given a presentation, given that one-line formula, this is what it really looks like. This is how those elements are put together. So it doesn't encode any more information than the presentation. It allows us to actually see it.
Right. Great, thanks.
Yeah. Thanks, sir. Yeah. So before we even define homomorphisms, an automorphism, students can understand, is a rewiring of a Cayley diagram. So there are 7 ways to rewire the cyclic Cayley diagram, and all of them. So this one is, well, and these things form a group. So this is the tripling map. It sends a red arrow. It sends a red arrow to 3 red arrows. This is the doubling map. It sends this red arrow to a double red arrow. And all of these are given by like doubling, tripling, quadrupling, etc. The automorphisms form a group. And if you take the integers mod 7 under multiplication, that's what the group is isomorphic to. So this group here, I claim, is generated by 3. So if you take 3 times 3 mod 7, you get 2. And so if you do the tripling map twice, you get the doubling map. 9 mod 7 is 2. Now 3 times 2, if you do the tripling map again, it is 6. So if you do the tripling map 3 times, this gets mapped to 6 arrows. And now 6 times 3 again is 4. So if you do it, this thing with the 4th is the quadrupling map, and then 4 times 3 is 5. If you do it the 5 times, you get this thing here. So this is that way to visualize the automorphism group, and you can construct the semi-direct product. And I'm not going to go into the details of C7 with C3 by taking, basically, you take C3, which is this group right here. You picture these things as like balloons. You blow up those balloons, and you stick in these 3 rewirings, 0, 2, 4, into these balloons. So here's the null rewiring. here's phi squared, and here's phi to the fourth, and then you reconnect things back up. So my students do this on the homework for several different groups before they have any idea what a homomorphism is. And in terms of automorphism, they just know it as a rewiring. It's like the doubling map or the tripling map. And so here's a construction of a semidirect product of C5 and C4. You take C4, you blow up these are balloons, you blow them up like this, you stick different rewirings in here, and then you reconnect them up. Now there's different ways of how you can stick rewirings. So this labeling map is phi to the 0, phi to the first, phi to the second, phi cubed. Well, there's another labeling map which you can do, which is phi to the 0, phi squared, phi to the 0, phi, which corresponds to this labeling. And this gives you a different semidirect product. So again, I can spend like 20 minutes on any one of these little topics in detail, but I'm just quickly going through because again, too many shiny objects. So this is a different semidirect product of these two groups. And here they are. So on my homework, I have my students, I say, tell me which one is which. This, oh, I will take you up on that, or if you want to, ever spend hours going over this stuff. Those two groups I showed you, one of them is the dicyclic group, and another one is these affine transformations of Z5. Which one is which? Well, one of those two groups has an element of order 10, and only one element of order 2. The other group has no element of order 10, but it has 5 elements of order 2. So you go back here and you say, well, let's try to find an element of order 10. So here's the identity. Now let's take B squared. B squared is blue, blue. So B squared has order 2. Let's do it again. B squared, so B, blue, 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 blue has order 2. So then let's ask around, what other elements, or are there any other elements that have order 2? Let's try red, red, blue. 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 That element has order 5. So what about blue, red, blue, red, blue, red, blue, red? That has order 5. So how many elements does this have of order? So you can figure out which one is which by looking at, is there one element of order 2 or 5 elements of order 2? Now, notice that I've highlighted this little thing here. This little crystal thing should remind you of like I call it a stalagmite. You know, in a cave, those things stick up from the bottom. This is a subgroup of D5. And you can tell because the subgroup lattice of D5 is sticking up from the bottom like a stalagmite. Mm-hmm. Now you see that copy of that sticking from the ceiling here like a stalactite. That's because that's a quotient. D5 is a quotient of this group. So that's something that I didn't actually really think about until I taught this not the first time, that subgroups and quotients, you can see them as they're stalagmites and stalactites in the lattice. So I emphasize lattices throughout this class. So we see these pictures all the time. So most books, you know, if they have pictures, it's a couple lattices, but they don't really emphasize it in this way. So here's a subgroup lattice of D4. You can think about, so this is the symmetries of a square. These are just the rotations. These are different Klein 4 groups. This is a 180 rotation, and just again shiny objects. Let's get to cosets. So a coset, so a subgroup. Here's a subgroup. A left coset is of the RH is of the form do R and then do the H arrows. Whereas a right coset, you start with the group H, and from each element, then you do R. Notice how you get to different places. So this is an example where this left coset is different than this right coset. So now here are the left cosets of that subgroup. Here they look like these little fragments that all have the same structure. And the right cosets, these two are the same, but the other two are scattered. So throughout this course and this talk, I'm going to represent it like this. So here is the partition of the group by the left cosets. The blue coset, I'm going to color a left coset blue if it's a right coset. So these two things are also right cosets. These two things are not. So here are the left cosets and here are the right cosets. Notice how this partition, those blocks are the same as those blocks. So they are blue. Now, you've probably heard of the normalizer of a subgroup, but it's, you know, definition that's not that memorable. I'm going to give it in a way you won't forget it. The normalizer of a subgroup is all of the elements that are in blue boxes. That's it. It's all of the left cosets that are right cosets. It's the things that are blue. Isn't that nice? I'm defining this before I define what a normal subgroup is. So just all the blue boxes. So here's a little cartoon. In general, you got a subgroup and it's got cosets, and here's the left cosets, here's the right cosets. The normalizer are the blue cosets, the union of them. So in terms of Cayley diagrams, here's D6. The cosets are the normalizers are the cosets that are reachable uniquely by a unique path from the subgroup. So to get here, I can either follow R from here or R to the 5th from there. There's 2 ways to get that there. But here, there's only one way. Either from here I do R cubed, or from there I do R cubed. So that's the normalizer. Now here's one of my favorite pictures. Here are 3 subgroups of the alternating group A4. And this shows the partition into left cosets. Now, what do you notice? All of the left cosets here are blue. This subgroup is normal. This is like, so first of all, every subgroup H is gonna, every subgroup itself is a left coset and a right coset, because EH is equal to HE. So if you multiply by the identity on either side, it doesn't matter. So every subgroup itself is blue. The question is, what else is blue? In the best case scenario, everything is blue. This is what a normal subgroup. In the worst case scenario, only the subgroup itself is blue and everything else is red. And then there's this in-between case where you might have 6 cosets and 2 of them are blue. So you see what these numbers are, 1, 4, and 3? That 1 out of 100% of the cosets are blue. 1 out of 4 cosets are blue. 1 out of 3 cosets are blue. This is really just a way to measure how far from normal a subgroup is. This is as normal as possible. This is fully unnormal. This is the worst possible case. And this is moderately normal, which is like a good description for where we are right now, sort of post-COVID-ish. So now you may say, why do we need these definitions? What good does this do? Hold that question. That's a good question. But first of all, look at these numbers: 1, 4, and 3. 100%, 1/4, and 1/3. Here's that subgroup lattice. N is conjugate to 1 other subgroup. H is conjugate to 4 other subgroups, and K is conjugate to 3 other subgroups. So the number of conjugates of a subgroup is, in some sense, a measure of how normal or unnormal a subgroup is. The more this thing fans out, the further it is from being normal. And these are the same measurement. So these things measure the same thing. Those numbers that I showed you, I actually define this thing, I call it the degree of normality, the reciprocal of these: 1, 1/4, 1/3. And that's how I define fully normal and moderately unnormal. I'm not going to do this slide, but that measures the same thing as to how wide these fans are. It's the same thing. And this is an immediate consequence of the orbit stabilizer theorem, but I throw this in a lot earlier because it really helps. This picture tells so much. Now, here's another way to think about this. If a group is normal, its normalizer is the whole thing. If it's fully unnormal, then the normalizer is the subgroup itself, and it's indexed to n, and you have n conjugates. If it's moderately unnormal, then the normalizer is in between, and it's index m, and you have m conjugates, not as many as possible, sort of in between. So now, here's it. So I'm going to define a group. I'm going to say that a group is a unicorn. So I'm going to push bases a little bit. You have this is a subgroup lattice of a mystery group of order 16. And I want to hypothetically imagine conjugating this group by a mystery element X. So if you take an arbitrary element X and you conjugate it, this is what you get. So this is the same group as that, but these things might shuffle. Now, this subgroup R squared is the only subgroup of order 4 that has 3 parents. These guys have 1 parent. So when you conjugate this, it can't hide. This is the only guy over here that has 3 parents. So it has to be a normal subgroup. This is the only subgroup of order 4 that has 3 kids. So if you conjugate this, it's got to go to another subgroup with 3 kids. So this conjugate, any conjugate has to be itself. This is normal. So any subgroup that is unique or has formally fixed by every lattice automorphism, I'm going to call a unicorn. So this is the only guy that has 1 parent and 1 kid. You conjugate it, it's got to go to itself. So I color the unicorns purple because unicorns are purple. And these things have to be normal. These also have to be normal because they are indexed 2. So in this mystery group, this mystery lattice, every subgroup has to be normal except possibly these 2. Now there's 2 possibilities. If these things if the conjugacy class of S is itself, then it's normal. Both of these are normal. Then this is central and the group is abelian. And I won't go into the details for why, but so if, in other words, if these 2 things are not conjugate, the group is abelian. The other possibility is if these 2 things are conjugate, then this is the conjugacy class. This is not normal. S is not abelian, and the group is not abelian. So there's 2 possibilities. We can almost narrow down what group this is, but there's 2 possibilities. I'm not saying both of these are actually possible, but turns out they are. So this is the subgroup lattice of that abelian group. Here's the generators. I won't verify that, but also it's the subgroup lattice of that. This is why I call it the semiabelian group. Not the same. These are 2 groups, one abelian, one not abelian, that have the same subgroup lattice structure. I didn't know that existed until honestly a couple of years ago. I don't think most students see that either. And you can really see why. I mean, so in my homework, I give them problems like this. So here are those 4 groups that we've seen, and I label these groups with like letters A, B, C, W, X, Y, Z, and then I put the negatives over here. And then I tell them to construct a table, a multiplication table, basically to generalize what I did with, remember the beginning of this talk, how I gave you this table. So I did that and that's a quotient. I have them do the same thing with those groups. And they really discover what a quotient is by doing that exercise here. And it turns out that these have the same quotient, dihedral, and these have the same quotient, abelian. So it's sort of this discovery before we even get to what quotients are. And again, I know I'm going fast, but there's too many shiny objects. So I think I will skip this. So this is conjugation preserved structure. I think I can, pictures of how, you can go over this in your own time if you want to. Here's another example. So here's that remember that group Dic6? I said, this is one you can't live without. This, you may recognize, maybe not, is the subgroup lattice of the dihedral group D3. So if you quotient out by this, you get the dihedral group. And now here are the conjugacy classes. Now I'm going to take 3 of my favorite elements in here. The first one is going to be R3. This is in a conjugacy class of size 1, and it commutes with everything. So it generates a size 2 subgroup, and it commutes with every single element in every single coset. This element is truly central. It is in the center of the group. Now, here's another element I'm going to take. I'm going to take R squared. This is in a size 2 conjugacy class. It does not commute with everything because these things are conjugate. This generates a subgroup of size 3. Here are the 4 cosets. And actually, R2 commutes with half of these elements. Conjugacy class of size 2 commutes with half of the elements in the group. S is in a conjugacy class of size 3. It commutes with 1/3 of the elements in the group. See that duality that we saw before? I know I'm going really fast, but I'm going to call that this element is central. It commutes with everything. This element is fully uncentral. It commutes with nothing other than powers of itself. Powers of itself. This element is moderately uncentral. It commutes with powers of itself, but also another coset of that group as well. This is just the orbit stabilizer thing. And we haven't done that yet. Even in my class, we haven't done that yet, but my students are seeing these connections. They're different neurons are firing that don't fire if you don't do these pictures. And I'll be honest with you, I understand this. I thought I understood all of undergraduate algebra a couple of years ago. I was so naive. I feel like I was colorblind, and I'm putting on glasses and seeing the world in focus and in color for the first time. I'm like, oh my God, that's really what's out there. Like, I really was an imposter, and I'll admit it. I did not know the stuff that I thought I was supposed to. So same thing. I'm going to skip this in the interest of time. Quotient groups. If you have a subgroup and it's normal, you can quotient out by it. This is an example. So remember, a subgroup is normal if all of the cosets are blue. And in this case, you can quotient out by it and you get a cyclic group. This does not work. If you try to quotient out by that, you do not get a Cayley diagram. In short, this is what, if the quotient works, this is what happens. This is a picture of what well-defined means. This is a picture of how well-defined this can fail. Again, I spend 10 minutes going over this in class, but I'm doing it for you now in 30 seconds. These are the sort of pictures that, like, I think every algebra book should have. For me, teaching algebra without these pictures are like teaching calculus without graphs. I mean, you could do it, but why would you do it? And the reason why we do it is because I learned it without pictures. And all the books don't have pictures except occasional sublattices. And there aren't any resources available with pictures. So that's basically why, like, we use the books that we learn from or variations of them. And so now I'm going to quickly go over the isomorphism theorems in my last few minutes. The first, and also every single book I've ever seen does the isomorphism theorems wrong. They are in the wrong order and there's the wrong number of them. So here's the real correct way to do the isomorphism theorems. The first one says all homomorphic images are quotients. If you have any homomorphism, what you are basically doing is you're taking the kernel, you're taking the cosets and you're shrinking them. You're doing a quotient map and then relabeling that. Every homomorphic image is a quotient. So what's the next? Here's a table way to see that. You take the Quaternion group. Here are the cosets. You shrink those and you relabel, and now you get the Klein-Ford group. Now, what's the natural thing to ask? If you know that every yeah, so I'll say more about in the chat. There's a book. So Nathan Carter has a fantastic book, Visual Group Theory. It's not it's a general audience book. It's not targeted for undergraduate mathematicians. It's a fantastic book though. But I am actually writing a book, and I'll get to that later. So if every homomorphic image is a quotient, what's the obvious thing to ask? What do we know about quotients? What's their structure? What are their subgroups like? What are their quotients like? So the second isomorphism there, which everyone calls the fourth, if they even include it, characterizes subgroups of quotients. Here's the dicyclic group. Again, I love this group. This group here's the center. This group is normal. Here's the quotient by it. You can see there's the quotient. This is the map from the dicyclic group to the dihedral group, the symmetries of the triangle right here. Now the elements in here, I call them shoeboxes. They're cosets. We know what the subgroups of these are. So here are these 6 shoeboxes right here. Here's a subgroup of these 3 shoeboxes. Now let's take these shoeboxes, let's take the lids off. Here's the picture we get. Those 3 shoeboxes that are in this subgroup, again, this guy, and this guy, here they are right here. Here's the shoeboxes with the lid off. Now, if we empty out the boxes, we get this, and this shows you how the subgroups of the quotient are just quotients of the subgroup. This is what should be the second isomorphism theorem. Okay, so here's a lattice way to see that. If you take the dicyclic group and you quotient out by this, what you're really doing is you're taking this stalactite and you're chopping this off. Here are the boxes with the lids open. Here are the boxes with the lids closed. I use these words in class. I talk about boxes. I talk about stalactites. And I use I talk about parents and children, etc. Now, the third isomorphism theorem, this one they got right by dumb luck because a random permutation of the isomorphism theorem will have a fixed point. Oh,
rare.
By the way, subgroups this is normal because that is normal in the original group. This is normal because that's normal. This is normal. So that the normal subgroups in the quotient are the normal ones in the original. So the obvious thing, the next thing to ask is, well, if we know what the subgroups of quotients are like, what are the, and we know which ones are normal. What do we get if we quotient by them? What's a quotient by a normal? So what's a quotient in a quotient group? And the answer is, here's two ways I like to see it. So this is sometimes called the freshman theorem, because this is so easy, even a freshman can do it. You just cancel the ends, but what does that really mean? Well, if you take G and you quotient out by N, you get this group right here. Now, if you quotient out by that, you get that thing. But what you basically are doing is, it's the same thing as if you had originally started with this and quotient out by H originally. So chopping off here and chopping off here to get here, and then chopping off there is the same thing as if you had chopped off here originally. And here's another way to think about this. I won't go into the details of that. And then the fourth isomorphism theorem, typically called the second, I think it comes after these. It's what happens when you quotient a product AB times a factor. Now your freshman is going to get this one wrong. They're going to say, oh, cancel the B's, you get A. No. Books often have this picture. Here's a better picture. It's just saying this lattice right here is the same structure as that lattice. This is like the only Goldilocks picture I could find. It's really hard to find one that's big enough, but not too big and not too small. Okay, so I don't have much. Oh, and then there's a fifth isomorphism theorem, which says the operation of subgroups and quotients commute. So if I take this group and I chop and I take this subgroup, that's chopping things off below here. And then if I quotient by here, I'm pruning above. So chop here, chop there, I get this. But if I do this in the opposite order, if I first quotient, I get remember the alternating group? Here it is, the quotient. I first quotient, then I take a subgroup. I get the same thing. Not only are they isomorphic, they are the same. If anybody knows matroids, deletion and contractions commute, and they also represent stalactites and stalagmites on a certain lattice. Nobody puts those things together. It's the same thing. It's upsets and downsets. Okay, so I have 5 minutes left. I have to get a group actions. This is how most books define group actions. This is a terrible, terrible way. I've had students tell me, grad students, that I've never really understood what a group action is. A group action is a really easy concept if you phrase it the right way. And so here's how I'm going to phrase a group action. Imagine you have a switchboard, like you're driving a plane. Every element of the dihedral group has a button. So the dihedral group, every time there's a button, and every time you press a button, you permute, you shuffle this set of squares in the obvious way. Now, here's the only rule for a group action. There is an A button. Every time you press the A button and then the B button, you better get the same thing as pressing the A, B button. That's it. Press the A button, press the B button. It's the same thing as pressing the A, B button. What you're really saying is it's a homomorphism. This is pressing the A, B button is pressing the A button and pressing the B button. That's it. Visually, this action it's like a Keeley diagram, but there's collapsing. And now every group action really has 5 fundamental features. The orbit is what elements can you get to? It's a connected component. The stabilizer of an element says what buttons don't move you. And the fixed point set of a group element says, of a button says, when you press this button, what things don't move. If you think about these definitions in terms of buttons, it makes things so much easier. And then the kernel of the homomorphism is just the set of broken buttons. The fixed points are the set elements that never move no matter how you press the buttons. So here's some examples. So here's the orbits. So it's fun to go through here and look at the stabilizer. So what elements fix this guy? Well, the identity does, but also if you rotate, and flip, you end up back here as well. And then the fixed point sets. So what's flipped by a flip? Flipping vertically or horizontally fixes these 3 things. So these are the fixed point sets. Now, what I like to do with these actions is I like to draw a table like this. And you can read off these things on the table. So the stabilizer of a set is just the columns tell you the stabilizers. What stabilizes this thing? Well, it's every check mark at G8S means G fixes S. So the stabilizers of this are the 4 elements that fix it. the fixed point set of this group element are the three things, are the columns or the rows. And the kernels and well, I'll talk about the kernels and the check marks later. But one thing you might notice, if you look at this, there are 24 check marks on this table. And if you divide that by the size of the group, which is 8, you get 3. 3 is the number of orbits. That's Burnside's, or what's sometimes called Burnside's lemma, or not Burnside's lemma. I call it the orbit counting theorem. It's a fundamental theorem, and it's just the average number of fixed points is just the number of orbits. And you can see that by just, and you can prove that basically by this table. So here's, I'm going to finish a couple more of this with just a couple pictures. Group actions. Remember I talked about conjugacy classes? You should draw these things with these action diagrams. Here are the conjugacy classes in D6. I showed you that orange and purple table. Here's what actually happens. So when you conjugate by R, you follow the red arrows, and when you conjugate by blue, you follow the blue arrows. And the stabilizers are the centralizers. Here's that fixed point. So here, the fixed points of this action are, well, actually, so there are 6 conjugacy classes. That's also 72 check marks divided by 12. You can also conjugate subgroups. So we talked about conjugating subgroups before. Here's a picture of that superimposed on the lattice. And so, here's the fixed point table. There's 5 conjugacy classes, 60. Now, the kernel is the row that has all check marks, and the fixed points are the columns that have all check marks right here. So it's fun to, I want to explain, groups act on cosets by multiplication. This is not a normal subgroup. If you try to quotient by it, you're going to fail. This is not a Cayley diagram. But if you collapse by the right cosets, what you are doing is acting on it by multiplication. You get this diagram. And this is fun to play with and analyze. And so, anyways, the last thing I want to say, I have 1 minute left. Solvable nilpotent groups. This is one of the classic things that, like, I learned in grad school. I didn't really fully understand, or I forgot. Any books, this is the definition of solvable, and this is nilpotent. What the heck does that mean and why? Do you have the right picture? So a group is solvable. So that the commutator subgroup is how far can you go down the lattice and get an abelian quotient? So what I'm highlighting here are the maximal abelian quotients, the largest abelian stalactites in these lattices. These are called the commutator subgroups. You can iterate this process. If you start here and you take the commutator subgroup, you get here. Now, if you do that again, you get down here. You do it again, you get down to the bottom. A group is solvable. So I say you are climbing down the lattice with these maximal abelian steps, and it's solvable if you get to the bottom. That's it. Now, nilpotent. Oh, and this is A5. This is not solvable, and these are the CELO subgroups, and it's fun you can analyze this in terms of the lattice. I won't do it. But nilpotent means the opposite. It says, when can you climb up a lattice? Now, how do you climb up a lattice? You start at the bottom, and well, you go to the center, which is always normal. And then you quotient out by the center, and you get this subgroup. This is the Dihedralgroup group, and then you find the center of that, and you quotient out by that, and you get this. Now, this is the abelian, the center is the whole thing. So nilpotent means you are climbing up a lattice, and solvable means you're going down. And I don't have a fun characterization of nilpotent groups. Remember that totally unnormal subgroups? A group is nilpotent if it has none of those. That's a nice little way because you have that visualization of that as bad as possible. So I don't have time to talk about this is the last topic. I'll stick around if people want to know about this, but basically inner automorphism. So quotienting out by the center also describes the inner automorphisms. And here's a picture about this. And And then this is the automorphism groups, the quaternions. These are the inner automorphisms. These are the outer automorphisms. And if you collapse by the conjugacy classes, you get this diagram here. And the automorphism group is a semi-direct product. So this is something that honestly, I never understood this in grad school. Like I didn't, but if you visually, if you work your way through it, it's a beautiful thing. So that's basically all I have to say. I have some closing remarks. Going forward, I'm writing a book on this stuff. I need a title. So if you have any ideas, let me know. I had this great idea, postmodern algebra, and then I Googled it, but it's been taken. And then I realized that Joe Gallian's book is contemporary abstract algebra, which is like later in time in the art world than postmodern. So like, I need a title. Nathan Carter, who wrote Visual Group Theory, and Dana Ernst, who also teaches this way. We have discussed organizing a workshop or special session talking about how to teach this or how to share ideas. And, the examples we have, I'm sure some of you can come up with better ones or different ones, and I'd love to share. So if you like these ideas, spread the word. This is how word gets out. Like I post all of my stuff, homework slides on my website. You can check it out. You can download the source code. I guess I don't have the slide source code because I'm still working on them, but I can email you. So I'm going to write a book on this. Hopefully the MAA will publish it. But you know what? That's not ever going to take off unless slides and homework is available, because no one's going to make these slides from scratch. I mean, I've done them, but no one's going to teach this way unless they have materials. So that's why I will always post these things publicly. And yeah, so I don't know. I'm open to feedback, but one thing that I've learned is when I start thinking about these things visually, there's no going back. Like if you decide to take this approach, you're taking the red pill. So I want to invite you to come with me, join me, come from the dark side, take the red pill, and this is the most fun I've literally ever had in the classroom. So I encourage you, if you're on the fence, if you're nervous about this, I'm happy to help you. I'm happy to talk with you over Zoom or email. Take the red pill. It's so much fun. So if you got questions, let me know. I can stick around here, I think, as long as I want. Alex, I'm supposed to have a research meeting with you in a few minutes, but I'll join a little later.
All right, please join me in thanking Matt for a very beautiful session. Just to wrap up briefly before we stop our recording, next week we've got motivating category theory with combinatorics with Joe Muller. I don't think Joe is here, so we can't get an announcement, but it's up on the screen. Hopefully you'll join us next week. And we'll stop our recording.
Yeah, thanks for coming, guys.